Okay, welcome to another presentation on waves. This is basically just a series of pictures. So every slide is going to be some example of a wave behavior like reflection, refraction, and I'm going to have three pictures. Will be a sound example, and one will be a light example, and one will be an example of a mechanical wave. And not all of these were covered in the other lecture. So let's start with the basic one, reflection. So what you see in the top left here is an overhead picture of a water tank where waves are being produced above the picture, and then they come in and then they hit this diagonal wall here, and they've drawn a black line here, which is the normal, right? The normal to the line. And you can see that the wave fronts coming in then reflect out at an equal angle, right? So this is a wave tank, so that's a mechanical wave. Over here we have a piece of glass, a reflecting surface, and we have a laser pointer, and you can see once again the incoming and outgoing rays, the incident and reflected, are coming in and out at equal angles. And over here you have an example from sound. This is sonar. So sonar is people send out sound waves, and then they listen for the echo, and then they figure those two distances are the same, and then they divide the time by 2 and multiply by the speed of sound and figure out how far away things are. Okay, scattering is a type of reflection, I guess. It's basically when a wave hits an obstacle that's around the same wavelength as itself, instead of reflecting in the usual way, since the surface is not bigger than the wave, it reflects in all different directions, and that's what scattering is. So the top one, this is something you'll see in theaters often, like behind the stage, or in this case it's on the sides. You'll see these curved surfaces. Sometimes they're hanging from the ceiling, and these are about the size of the wavelength of sounds that you expect to hear in a theater production or an orchestra performance. And what this does is it prevents the sound from reflecting nice and neatly, so that you don't have certain seats that get constructive and destructive interference, where it's loud or quiet, and also you don't hear an echo, so you don't think the sound is coming from somewhere else. Instead, the scattering, just keeps a uniform distribution of the sound waves in the room. The most famous example is scattering is the reason why the sky is blue. So let me walk you through that really quickly. The sun is actually producing all of the colors. It's an entire spectrum of electromagnetic radiation centered on visible light, but it certainly has all the colors in there. The sunlight is white. And as the colors hit the atmosphere, though, it does encounter these small particles, right? Nitrogen molecules and oxygen molecules. And it turns out that blue light, the shorter wavelength light within the visible spectrum, is more closely aligned to that nitrogen molecule's size, basically. And so it gets preferentially scattered. So all the light is getting scattered a little bit off these molecules, but blue light is scattered more to a greater degree. And so when you look up here into the sky where there's no light source, why do you see any light at all? You have to ask yourself, where's that blue light that's coming into your eyeball coming from? It's actually coming from a ray from of sunlight that would never go into your eye, that's going out over the horizon. And to the extent that anything is coming in your eye, it's coming from light that was scattered off those molecules. This, of course, is the exact same reason why sunsets and sunrises are red. It's because you're looking at the remainder of that light, right? That white light that's coming from the sun has had all the blue end frequencies preferentially scattered out. And so which ones are coming through and cutting through and getting to your eyes are the longest wavelengths, the least scattered ones, the red. So sunsets are red for the same reason that the sky is blue. It's all because of light scattering. Over here you see some scattering. This is a seismograph of earthquake waves that have scattered off of mineral deposits underground. Okay, refraction. So here's the classic light refraction, right? Laser pointer or laser light of some kind in air, and then it has to slow down to go through this glass or plastic. As it slows down, it pivots away from the normal, and then when it comes back out from slow to fast, it pivots away from the normal. I'm sorry, here it pivots towards the normal. Did I say the right thing? And then here it's pivoting away from the normal as it goes from fast to slow and then slow to fast. Over here, what you have is this is an overhead view of a water tank again. So these are ripples of water. So this, I don't know if the source is on the left or the right, but you can see there's this kind of triangular, rectangular, submerged object here, which makes the water a little shallower. And so that affects the speed that the ripples and the waves can go through there. And so you can see that that change in speed actually bends the waves where the obstacle is underwater. Here's an effect that you may have noticed that you didn't know was refraction, but this is very apparent usually over like a lake or something like that, or a pond. And you can hear sounds on the other side very clearly in the morning, right? Because the cold water or the cold ground is keeping the air cold right above it, and yet the sunlight is warming up the air around it. So basically, you have warm air and cool air, which are like two different media, right? Sound travels a little bit faster in warm air. And so when you have that effect of the cold air on the bottom, it tends to refract the sound towards the ground, which means that all these sound waves that normally would never hit your ear, that would go out here into the upper part of the sky, they get refracted in, and you get an increase in amplitude in your ear. And so you can hear these sounds from far away very clearly. Of course, the opposite is true, and the opposite effect. Diffraction, so that on the right-hand side, you have your ocean waves here. These are natural, this is the actual black and white picture where you have some natural, like a natural harbor type setup where you have an opening between these rocks, and this is the ocean down here. And you can see actually the diffracted waves that are curving away from this opening and also from this opening, right? And you can even see some interference over here. It's a 2-for-1 slide. Here's a picture of sound waves. This is why you can hear people around corners, right? It's because the sound wave is comparable to the wavelength is comparable to the opening of the doorway, and so you get a lot of diffraction around here. And so even though you can't see them, you can hear them. To see them, you need really small slits. Like here's a very small opening with a light source on the other side, and then if you look far away, you can see some diffraction here, right? You're not just getting an image of the single slit, the same width as the actual slit. You're getting, first of all, multiple slits, and they're all a little bit wider, and you can see they're getting wider and wider as they get farther and farther away, and that's because the light waves are spreading out also. Resonance is a specific thing that happens with waves. When waves are coming in and then they hit an object whose natural frequency of oscillation is the same as the wave that's coming in. So the classic example is the opera singer that can break glass with their voice, right? There's a Mythbusters on this. If you look it up, this is actually true, right? If you match the pitch to the natural vibration frequency of the wine glass and you're loud enough, you can get this to vibrate. And of course, glass doesn't like to vibrate, and eventually it will break, right? Because as it absorbs more and more energy, the amplitude gets bigger and bigger, right? If you push somebody on a swing, you actually have to push them at the resonance frequency or else it doesn't work, right? And this is how antennas work, right? So when you're receiving radio signals or Wi-Fi signals of any kind, what happens is you tune in to the frequency that you want to hear by the frequency. All these different frequencies of electromagnetic radiation are making electrons dance around in the wire in your antenna, and then you pick out the frequency that you want of the current that's being stimulated by the frequency of electromagnetic radiation that you care about. Constructive and destructive interference. Here you have two sources of water waves, and you can see when the waves meet each other, peaks to peaks and troughs to trough, you get big waves, and so you get this, high, low, you get constructive and destructive interference pattern here. If you look down, oftentimes you can see this like at a gas station or something where you got a puddle of water and a thin layer of oil or gasoline on top. What you're seeing is the interference between a reflection of light off the top surface of the oil, the thin sliver of oil on top of the water, and a reflection off the bottom surface of that oil, right? And those are two slightly different distances apart, and so you get those two light rays entering your eye and doing constructive or destructive interference at different wavelengths, and so you see these different colors, even though the object itself is not colored and the light coming in is all the colors. Noise canceling headphones work the same way. So every noise canceling headphone actually has a microphone and a speaker in it. So the microphone listens to the incoming wave and then on the fly creates an inverted wave. And so noise canceling headphones are actually creating more sound, right? But because the sound is out of phase, you get the peaks on top of the troughs and they cancel out, right? And so they can selectively do this for noise outside and then not affect the music you're listening to. Or if it's like for a factory, they could just get rid of whatever frequency range the equipment is in that's so loud and damaging to your ears. Standing waves is also an example of constructive and destructive interference, right? It's when you have a pattern of constructive and destructive. Right here you have constructive, then a node here of destructive, and then another constructive, then another destructive. So anytime you have a standing pattern of this, this is actually made out of a wave traveling up and down, interfering with itself. Here's a sound wave when you blow over the open bottle of like a can of soda or something, or a bottle of soda or something like that. you can get this big resonance cavity, and that actually corresponds, the frequency that you can get out of there corresponds to the length of the tube here. So that's a standing sound wave in there. This is a standing mechanical wave on a string, right? All musical instruments, basically, when you're playing a certain pitch, it's because you're creating a standing wave at that frequency. And you can do it with light. Light, it's a little bit harder to do, but if you take, this is a classic experiment that undergrad physics majors do. It's called the Michelson-Morley experiment. You take some light and you split it into two beams, and then those two beams travel two slightly different distances. And then when they bounce back off of these mirrors and come back together, you can see alternating bright and dark spots if it's a single color thing, or if it's white light, you can see constructive and destructive interferences based on the different wavelengths there. The Doppler effect in all three cases. So here's an interesting one for mechanical waves. Next time you see a boat in the water that's traveling slow, or this is a duck, right? He's traveling slightly below the wave speed in the water. Most boats will actually travel faster than the speed of the wave. So I'll show you a picture on the next slide of that. But you can see the wave fronts are bunched up in front, been highlighted in blue here. So there's your high frequency Doppler shift. And then behind them, the ripples are farther apart. That's your low frequency Doppler shift. This is the example that we already talked about with a moving car. When a car passes you on the road, you get that, that high to low sound, and that's, of course, because you're going from high frequency Doppler shift to a low frequency Doppler shift when it passes you. It's very dramatic. Happens with light too, but with light it's very hard to detect because the speed of light is so fast. So you need to be going an appreciable an appreciable speed as a fraction of the speed of light for your eyes to ever be able to detect it. And so this picture is a little misleading. I don't think there are any cases where you would actually see the red or blue shift, but it's used often in astronomy because in that case you do have very high relative velocities, and of course you also have scientific equipment that can do it. When a policeman is using their radar gun, right, that they're using the Doppler effect, right? The radar gun they point at you is shooting out radio frequency, electromagnetic radiation that the gun knows the frequency of. It bounces off of your car because your car is either usually it's moving towards the police officer. It will then receive that signal that's bounced off your car and compare it to the original frequency, and however much it's been shifted to higher frequency by will tell you how fast you're going. Shock waves are also, this is an extreme example of the Doppler shift. So, right, this is what you see in boats all the time. When you're going faster than the speed of the wave in there, you get this classic V shape. That's a shock wave, right? An extra high amplitude wave because of the constructive interference of all the waves getting piled on top of each other. Of course, that's a sonic boom if it's for sound. And the surprising thing is it can happen for light as well. Charged particles that are accelerating, of course, create light. If you have a charged particle that is actually traveling faster than the speed of light, it will slow down. As it slows down, it will be releasing a shock wave of light. It's actually blue light. It's called Cherenkov radiation. That may sound odd to you because it can happen and cannot happen in outer space, right? Nothing can go faster than the speed of light in outer space. But you can imagine a case where you have, and this does happen, charged particles in outer space going 99.99% the speed of light in outer space. Those charged particles hit the Earth's atmosphere where the speed of light is significantly slower. It's like maybe 10% slower or something like that. And now these charged particles are actually violating the speed of light in air. And that's when you can generate Cherenkov radiation. This is actually, there's plenty of examples of this. Dispersion is where you get rainbows from. Dispersion is refraction, but it's a kind of refraction where the material is actually slowing down, has a different effect on the speeds of different frequencies, right? So for instance, a prism or a water droplet actually slows down blue light more than red light. And so when you get that refraction, when you go from air to water or air to a prism, you, since the blue light is slowing down more than red light, you get a greater angle of refraction. And so the light frequencies actually become separated out from the white light. And when they come out, they're all separated and you get that rainbow, right? So this happens with sound waves. This is how your cochlea, this is the rolled up tube of fluid behind your eardrum. They've straightened it out here. And so you can sort of imagine it as being a linear tube. The diameter of it's changing slightly. And so the different frequencies that come in will actually fizzle out at different points and stimulate different nerve cells inside your cochlea at different points, right? And that's how the frequencies are separated. Over here, someone has struck a wire that has varying densities, and so you can see the frequencies get separated out here on that mechanical wave. Okay, well, there's some examples of the three different classic types of waves undergoing these various forms of wave behavior.